The James Webb Space Telescope was not built to surprise us. It was built to confirm, to refine, to add decimal places to what we already believed. Instead, within months of turning on, it began returning data that did not fit comfortably inside existing models. Not dramatic explosions or cinematic events, but quiet, stubborn measurements. Numbers that were too large, structures that were too mature, chemical signatures that appeared where theory said they should not. This telescope does not take pictures the way your eyes do. It dissects light. It measures how atoms vibrate, how molecules absorb energy, how dust scatters infrared radiation across billions of years. Every discovery from Webb begins as a spectrum, a redshift value, a signal buried in noise. And that is why its discoveries matter. Because they are not opinions, they are measurements. What you are about to hear is not a list of pretty images released by NASA. It is a sequence of observational results, some expected, many unexpected, that are quietly forcing astrophysicists to revisit how fast galaxies form, how stars ignite, how planets assemble, and how black holes grow. These are not theories, these are observations. And once an observation exists, physics has no choice but to deal with it. The first thing James Webb did was look deeper into the early universe than any telescope before it. Using infrared wavelengths, it bypassed cosmic dust and red-shifted light that made the earliest galaxies invisible to Hubble. When astronomers processed the first deep-field images, they did not see what simulations predicted. They saw galaxies that were too bright, too massive, and too well-structured for their age. According to standard cosmological models, galaxies in the first few 100 million years after the Big Bang should be small, irregular, and chaotic. Star formation should be inefficient. Heavy elements should be rare. Instead, Webb detected galaxies at redshifts greater than 10 that already showed clear disk-like structures and unexpectedly high stellar masses. Some of these galaxies appeared to contain billions of stars less than 400 million years after cosmic dawn. This immediately created tension, not controversy, tension, because the measurements were consistent across instruments. Near-infrared imaging showed the structures, spectroscopy confirmed distances, photometric redshifts aligned with independent estimates. To make these galaxies fit the models, astronomers were forced to consider extreme star formation efficiencies, unusually massive primordial gas clouds, or revisions to how quickly dark matter halos collapse and cool. None of these fixes are trivial. Each one impacts multiple areas of cosmology simultaneously. What makes this discovery particularly important is that Webb is not sampling rare objects. It is finding these galaxies in statistically significant numbers. That removes the possibility that we are simply seeing oddities or flukes. The universe, early on, appears to have organized itself faster than expected. And Webb did not stop there. When astronomers pointed Webb at regions previously imaged by Hubble, they found something else missing from earlier surveys. Not large galaxies, but small ones. Faint dwarf galaxies predicted by simulations had long been undetected, creating what is known as the missing satellites problem. Webb's sensitivity allowed it to detect these low-luminosity objects for the first time at high redshift. This matters because dwarf galaxies trace the distribution of dark matter. Their abundance and spatial arrangement test whether current dark matter models are correct. Early Webb results suggest that some discrepancies may be observational rather than theoretical, but not all of them. Some predicted structures still appear absent. This tells us that while Webb is filling gaps, it is also sharpening others. Another major class of discoveries comes from Webb's ability to analyze exoplanet atmospheres with unprecedented precision. Unlike previous telescopes, Webb can isolate specific molecular absorption features across a wide infrared range, allowing scientists to identify gases directly rather than infer them indirectly. In its first year, Webb detected carbon dioxide, water vapor, methane, and sulfur-based compounds in the atmospheres of multiple exoplanets. These detections were not marginal, they were clean, high signal-to-noise measurements. One of the most striking results came from observations of hot gas giants, known as hot Jupiters. Webb measured vertical temperature gradients, cloud structures, and chemical stratification in their atmospheres. These results confirmed that atmospheric circulation on these planets is far more complex than previously modeled. More unexpected were results from smaller planets. Webb detected carbon dioxide in the atmosphere of a sub-Neptune-sized exoplanet, providing the first direct measurement of this molecule in such a world. This confirmed that even relatively small planets retain thick atmospheres capable of complex chemistry. In one case, Webb observed a planet whose atmosphere showed an unusual depletion of methane combined with an abundance of carbon dioxide. This combination does not violate physics, but it challenges assumptions about chemical equilibrium under known temperature and pressure conditions. It suggests either strong photochemical processes or atmospheric mixing far more efficient than predicted. Importantly, Webb is not designed to detect life. It is designed to detect chemistry. But chemistry sets constraints, and the constraints Webb is measuring are forcing atmospheric models to become more detailed, more dynamic, and less simplified. Another critical discovery involved the direct observation of thermal emission from exoplanets. Instead of relying on starlight filtering through atmospheres, Webb measured the planet's own infrared glow. This allowed precise temperature mapping and revealed night-side temperatures higher than expected, evidence of efficient heat redistribution. This tells us that winds on these planets may reach extreme velocities, redistributing energy across hemispheres in ways that challenge current general circulation models. Again, these are not dramatic headlines. They are precise mismatches between observation and expectation. And those mismatches accumulate. James Webb's infrared vision has also transformed our understanding of star formation. Stars are born inside dense clouds of gas and dust that block visible light. Hubble could only see the outer layers of these regions. Webb sees through them. When Webb observed star-forming regions like the Carina Nebula and the Pillars of Creation, it did not just produce clearer images. It revealed embedded protostars previously invisible, complete with accretion disks and bipolar outflows. By counting these protostars and measuring their mass distribution, astronomers can directly estimate star formation rates. Webb's data suggests that in some regions, stars form more efficiently and more rapidly than earlier infrared surveys indicated. This has implications for how quickly galaxies convert gas into stars, especially in the early universe. Faster star formation changes the timeline for chemical enrichment, radiation feedback, and galaxy evolution. Webb has also detected complex organic molecules within star-forming clouds, including hydrocarbons and carbon-based compounds. These molecules form on dust grains under cold conditions and are later incorporated into planets. Their abundance and distribution provide clues about the chemical inheritance of planetary systems. Webb's observations suggest that complex chemistry begins earlier and persists longer than previously thought. Even more unusual were detections of water ice in unexpected environments. Webb identified water ice signatures in regions exposed to intense radiation where ice was thought to be unstable. This suggests that shielding mechanisms or grain properties may protect ice more effectively than models predict. These findings affect not only star formation theory, but also planet formation scenarios. The availability of water and organics during early stages influences the composition of future planets. One of the most technically significant contributions of the James Webb Space Telescope comes from its observations of supermassive black holes in the early universe. Prior to Webb, quasars at very high redshift were known to exist, but their host galaxies were difficult to resolve. Hubble could detect the bright quasar light, but not the surrounding structure. Webb changed this. Using near-infrared spectroscopy, Webb separated the emission of early quasars from their host galaxies and measured both stellar mass and gas dynamics. In several cases, Webb observed black holes with masses exceeding 1 billion solar masses less than 700 million years after the Big Bang. These measurements were reported by multiple teams using independent datasets, including observations published in the Astrophysical Journal Letters and NASA's early release science reports. The problem is not that these black holes exist. The problem is how fast they grew. According to standard accretion theory, black holes grow at a rate limited by radiation pressure, known as the Eddington limit. Even assuming continuous accretion at this maximum rate, forming billion solar mass black holes so early requires either very massive initial seed black holes or alternative growth mechanisms. Webb's data strengthens this tension by showing that some host galaxies appear relatively underdeveloped compared to the mass of their central black holes. This challenges coevolution models, where black hole growth and stellar mass assembly proceed in lockstep. Several hypotheses are now being tested, including direct collapse black hole seeds formed from pristine gas clouds, super-Eddington accretion phases, or modified early feedback processes. None of these ideas violate known physics, but all require adjustments to existing galaxy formation frameworks. Importantly, Webb's measurements rely on spectral line widths, ionized gas diagnostics, and continuum fitting across multiple wavelengths. These are not single-image interpretations. They are multi-parameter analyses, cross-checked by different teams. In some cases, Webb also detected broad emission lines indicating active galactic nuclei in galaxies previously classified as star-forming. This suggests that early black hole activity may be more common than previously estimated, affecting reionization and early heating of the intergalactic medium. Another major scientific advance comes from Webb's direct observations of protoplanetary disks. These disks of gas and dust around young stars are the sites of planet formation. Prior infrared observatories could detect disks, but Webb can resolve their internal structure and chemistry. Using its mid-infrared instrument, Webb detected detailed silicate features, water vapor, carbon monoxide, and complex hydrocarbons in disks at various evolutionary stages. These observations, reported by the Webb Disk Survey teams and NASA's Cycle 1 programs, show that disk chemistry evolves rapidly, sometimes within a few 100,000 years. One particularly important result was the detection of water vapor in the inner regions of disks around Sun-like stars. These are precisely the regions where rocky planets form. Previous models suggested that water might be scarce in these zones due to high temperatures. Webb's data shows otherwise. This implies that water delivery to terrestrial planets may begin much earlier than expected, potentially altering timelines for habitable planet formation. Webb also revealed gaps, rings, and spiral structures in disks with unprecedented clarity. These features are often interpreted as signatures of forming planets interacting with the disk material. In several systems, Webb detected such structures in disks younger than 1 million years, suggesting that planet formation begins almost immediately after star formation. The dust grain sizes inferred from Webb's spectra indicate rapid grain growth, another essential step towards planet formation. Larger grains settle toward the disk midplane, promoting the formation of planetesimals. Webb's results suggest that this process is highly efficient, even in environments previously thought to be unfavorable. These observations are now being incorporated into updated disk evolution models and compared with ALMA millimeter wave data, providing multi-wavelength confirmation. James Webb has also reshaped our understanding of cosmic dust itself. Dust is not a minor detail in astrophysics. It regulates star formation, shields molecules, reprocesses radiation, and alters galaxy observations across cosmic time. Webb's infrared sensitivity allows it to measure dust composition and temperature directly. Early Webb studies of distant galaxies revealed surprisingly large amounts of dust present less than 1 billion years after the Big Bang. These results were published in Nature Astronomy and discussed extensively in NASA technical briefings. This is unexpected because dust is primarily produced by evolved stars and supernovae. In the early universe, there should not have been enough time for dust production to reach the levels Webb is detecting. One possibility is that dust formation in supernova remnants is more efficient than previously believed. Another is that grain growth in dense interstellar environments proceeds faster under early universe conditions. Webb's spectra show features consistent with both carbonaceous and silicate dust, indicating a mature dust population. Webb also detected dust-obscured star formation in galaxies that appeared relatively quiet in visible light surveys. This means earlier estimates of cosmic star formation rates may have been systematically underestimated due to dust hiding activity from optical telescopes. In addition, Webb observed dust emission in regions exposed to intense ultraviolet radiation, where dust survival was considered unlikely. This suggests that dust grains may be more resilient or continuously replenished. One of the most consequential scientific contributions of the James Webb Space Telescope concerns the epoch of cosmic reionization. This period, roughly between 400 million and 1 billion years after the Big Bang, marks the transition of the universe from a neutral state to one where hydrogen became ionized by the first luminous sources. Prior to Webb, observations of this era were sparse and indirect. Webb's sensitivity to faint infrared light has allowed astronomers to directly observe galaxies that likely contributed to reionization. Using spectroscopy, Webb detected strong emission lines such as Lyman alpha, H beta, and oxygen lines in galaxies at redshifts above 7. These detections were reported by multiple collaboration teams, including results published in Nature and the Astrophysical Journal during Webb's first observation cycles. What stands out is not just the detection of these galaxies, but their physical properties. Many appear compact, intensely star-forming, and low in metallicity, conditions favorable for producing large numbers of high-energy photons capable of ionizing hydrogen. Webb's data suggests that small, faint galaxies may have played a larger role in reionization than previously estimated. At the same time, Webb observed galaxies with surprisingly strong oxygen emission lines very early in cosmic history. Oxygen is produced by massive stars and dispersed by supernovae, meaning these galaxies must have experienced multiple generations of star formation in a short period. This rapid chemical enrichment challenges simple models of early galaxy evolution. Webb also detected variations in ionization statuses among early galaxies, implying that reionization was patchy rather than uniform. Some regions of the early universe appear ionized earlier than others. This spatial variation had been predicted by simulations, but Webb provided the first observational confirmation at this level of detail. These measurements are now being used to refine numerical models of reionization, incorporating realistic galaxy populations rather than idealized sources. The result is a more complex but more accurate picture of how the early universe transitioned into its current transparent state. Another area where Webb has delivered unexpectedly strong results is in the study of stellar populations and metallicity evolution. Metallicity refers to the abundance of elements heavier than hydrogen and helium, and it is a key tracer of stellar processing over time. Webb's spectroscopic capabilities allow astronomers to measure metallicity in distant galaxies with precision previously impossible. Early results show a wide range of metallicities in galaxies at similar redshifts, suggesting diverse evolutionary pathways rather than a single universal growth pattern. Some early galaxies exhibit extremely low metallicity, consistent with being dominated by first-generation or near-first-generation stars. Others show metal enrichment comparable to much later galaxies, indicating rapid and efficient star formation. These observations were reported by teams using Webb's NIR-SPEC instrument and published in journals such as Monthly Notices of the Royal Astronomical Society. The data suggests that early galaxies experienced bursts of star formation followed by feedback-driven pauses, rather than smooth, continuous growth. Webb has also been used to search for population 3 stars, the first generation of stars formed from primordial gas. While no unambiguous population 3 star has been directly detected, Webb has identified candidate galaxies whose spectral signatures are consistent with very hot, massive stars lacking heavy elements. The absence of a definitive detection is itself informative. It places constraints on how long population 3 stars existed and how quickly they enriched their surroundings. These null results help narrow parameter spaces in early star formation models. In addition, Webb's stellar population studies have refined estimates of stellar mass-to-light ratios in early galaxies, improving calculations of total stellar mass across cosmic time. This has downstream effects on dark matter halo modeling and galaxy clustering analyses. James Webb has also produced scientifically important results through what it did not find. These null and unexpected results are rarely highlighted in public releases, but they play a crucial role in refining theory. One example involves the search for methane in certain exoplanet atmospheres. In several targets where methane was predicted to be abundant based on temperature and equilibrium chemistry models, Webb detected little to no methane. These findings were reported in NASA technical briefings and detailed in the Astrophysical Journal letters. This absence suggests that photochemical destruction, vertical mixing, or non-equilibrium chemistry is suppressing methane formation.
These processes were known, but Webb's data shows they may dominate under a wider range of conditions than previously assumed. Another null result concerns debris disks around mature stars. In some systems where infrared excess suggested large amounts of warm dust, Webb detected less emission than expected. This implies either rapid dust clearing or differences in grain composition that affect infrared emission efficiency. Webb has also failed to detect expected signatures of certain molecular species in star-forming regions, prompting revisions to chemical reaction networks used in astrochemical models. These revisions affect predictions of molecule formation rates across a range of environments. Even in cosmology, Webb's null results matter. In some deep fields, the number density of faint galaxies does not rise as steeply as certain models predicted. This suggests limits on how many low-mass galaxies formed at early times, constraining dark matter and feedback models. These results highlight an important aspect of Webb's contribution. It does not just confirm or refute ideas, it narrows them. It reduces uncertainty by removing possibilities.
A large fraction of James Webb's discoveries are tied directly to the performance of its individual instruments, each revealing different aspects of the universe that were previously inaccessible. One of the most productive instruments so far has been NIRCam, Webb's primary imaging camera. NIRCam operates in the near-infrared and was crucial for identifying early galaxy candidates, resolving star clusters, and mapping gravitationally lensed systems. Using NIRCam, Webb observed massive galaxy clusters acting as natural gravitational lenses. These clusters magnify background galaxies, allowing Webb to study objects that would otherwise be too faint to detect. In several lensing fields, Webb identified galaxies with inferred redshifts greater than 12, corresponding to less than 350 million years after the Big Bang. These candidates were later followed up with spectroscopy to confirm distances, as reported in NASA Cycle 1 lensing survey papers. NIRCam imaging also revealed detailed substructures in galaxies previously seen only as faint smudges. Spiral arms, bars, and star-forming clumps were resolved in galaxies at intermediate redshifts, indicating that disk instabilities and internal dynamics were already established relatively early. These observations challenge the idea that well-ordered galactic structures are a late-stage phenomenon. Closer to home, NIRCam mapped stellar populations in nearby galaxies with extreme clarity, allowing astronomers to separate different generations of stars based on color and brightness. This has improved distance measurements and refined stellar evolution models, particularly for low metallicity stars. Perhaps most unexpectedly, NIRCam detected transient phenomena such as stellar outbursts and variable sources in distant galaxies during deep field observations. These incidental detections provide new opportunities to study stellar variability across cosmic time. Another instrument that has reshaped astrophysics is NIRSpec, Webb's near-infrared spectrographer. NIRSpec can obtain spectra of hundreds of objects simultaneously, making it a powerful tool for statistical studies of galaxy populations. With NIRSpec, Webb has measured precise redshifts, gas velocities, ionization states, and chemical abundances in early galaxies. These measurements confirm that many early galaxies are rotating systems rather than dispersion-dominated clouds, indicating that angular momentum was already playing a major role in galaxy formation. NIRSpec data also revealed extreme emission line galaxies with unusually strong oxygen and hydrogen lines. These galaxies exhibit star formation rates far higher than expected for their mass, suggesting episodic starburst behavior. Such objects were predicted by simulations but rarely observed before Webb. In addition, NIRSpec enabled the first detailed studies of gas inflows and outflows in early galaxies. By measuring Doppler shifts and line asymmetries, astronomers detected evidence of feedback from massive stars and black holes shaping galaxy growth even at very early times. These results were published in the Astrophysical Journal and presented in NASA instrument team briefings. NIRSpec has also been instrumental in exoplanet science. By analyzing transmission spectra during planetary transits, it provided precise measurements of atmospheric composition, cloud coverage, and pressure-temperature profiles. These measurements are now used as benchmarks for atmospheric models. Importantly, NIRSpec has confirmed that some exoplanet atmospheres are chemically heterogeneous, varying with altitude and longitude. This complexity was largely inaccessible before Webb. The Mid-Infrared Instrument, or MIRI, has extended Webb's reach into longer wavelengths, revealing phenomena invisible even to near-infrared observations. MIRI is especially sensitive to cooler objects in thermal emission, making it ideal for studying dust, debris disks, and cold exoplanets. MIRI observations detected thermal emission from exoplanets at temperatures lower than previously observable, allowing direct constraints on planetary cooling rates. These measurements were reported in early Webb exoplanet papers and are already influencing models of giant planet evolution. MIRI also mapped dust distributions in galaxies and star-forming regions with exceptional detail. In several nearby galaxies, MIRI revealed networks of filamentary dust structures tracing shock fronts and stellar feedback. These structures were only hinted at in earlier Spitzer data. One particularly important result involved the detection of polycyclic aromatic acids, or PAHs, in both nearby and distant galaxies. PAHs are large organic molecules that trace star formation activity. Webb showed that PAH emission behaves differently in low metallicity environments than models predicted, affecting how astronomers estimate star formation rates. MIRI also observed debris disks around mature stars and detected temperature variations within them, suggesting ongoing collisional processes. These results help constrain the late stages of planetary system evolution. In some cases, MIRI failed to detect expected warm dust emission, implying rapid disk clearing or altered dust grain properties. These null detections are now being incorporated into disk evolution theories. Beyond distant galaxies and exoplanets, the James Webb Space Telescope has produced a set of highly precise discoveries within our own solar system. These observations were not intended as headline science, yet they have delivered some of the clearest infrared data ever obtained for planetary atmospheres, moons, rings, and small bodies. Webb observed Jupiter's atmosphere across a broad infrared range, revealing detailed structures in its upper atmosphere, including auroral emissions linked to its magnetic field. Spectral measurements identified emissions from molecular hydrogen and ionized species, allowing researchers to quantify energy transfer from the magnetosphere into the atmosphere. These observations, released by NASA's planetary science teams, provided new constraints on how Jupiter's upper atmosphere is heated, an open problem for decades. Webb also detected previously unresolved features in Jupiter's faint ring system, confirming the presence of fine dust produced by impacts on small inner moons. This level of detail was not accessible to prior infrared observatories. Saturn was observed to measure atmospheric composition and thermal structure. Webb detected spatial variations in temperature and gas abundances, refining models of seasonal atmospheric circulation. For the first time, infrared measurements of Saturn's rings revealed temperature differences linked to particle size and composition. Perhaps most unexpected were Webb's observations of Neptune. The telescope detected strong methane absorption and revealed high-altitude clouds with clarity not achieved since the Voyager era. Webb also resolved Neptune's faint rings, confirming their infrared brightness and providing updated constraints on particle properties. Moving to moons, Webb observed Titan, Saturn's largest moon, and detected spatial variations in methane clouds and organic haze layers. These observations, published by NASA and ESA teams, help refine climate and circulation models for Titan's thick atmosphere. Webb also observed icy moons such as Europa and Enceladus, searching for surface composition signatures. While no direct plume activity was confirmed in these observations, Webb detected spectral features consistent with surface ice mixed with salts and organic material. These results provide boundary conditions for future missions rather than speculative conclusions. James Webb has also transformed the study of stellar remnants, objects left behind after stars exhaust their fuel. Webb observed planetary nebulae with unprecedented infrared detail, revealing complex shell structures formed by episodic mass loss. These structures had been suggested by models, but never observed so clearly. In several planetary nebulae, Webb detected concentric rings of dust and gas, indicating that mass loss from dying stars occurs in pulses rather than smoothly. These findings were reported in the Astrophysical Journal and help constrain late-stage stellar evolution models. Webb's infrared sensitivity also allowed it to study supernova remnants in detail. Observations of remnants such as Cassiopeia A revealed spatial distributions of heavy elements like silicon, sulfur, and iron. These maps provide direct evidence of asymmetric explosion mechanisms in core collapse supernovae. In addition, Webb detected freshly formed dust within supernova remnants. This confirms that supernovae can be efficient dust producers, helping to explain the large dust masses observed in early galaxies. These results support and extend earlier findings from ALMA, but with improved chemical specificity. White dwarfs were also observed to study debris from disrupted planetary systems. Webb detected infrared excesses around several white dwarfs, consistent with dusty disks formed from tidally disrupted asteroids. Spectroscopic analysis revealed metal-rich material, offering direct evidence that rocky planets survive stellar death and are later destroyed. These observations provide constraints on the long-term stability of planetary systems and the chemical composition of exoplanetary material. A separate class of Webb discoveries comes from its ability to revisit classic astronomical targets and remeasure them with far greater precision. These comparative studies are scientifically important because they test the consistency of earlier results. Webb reobserved star-forming regions previously studied by Spitzer and Hubble, revealing embedded sources and dust structures that were entirely missed. These differences are not due to reinterpretation, but to wavelength coverage and sensitivity improvements. In galaxy surveys, Webb has revised star formation rate estimates by directly measuring infrared emission rather than relying on indirect tracers. In several cases, star formation rates were found to be significantly higher than earlier optical estimates. Webb also remeasured distances to nearby galaxies using infrared standard candles, improving calibration of the cosmic distance ladder. These results affect estimates of the Hubble constant, although Webb's role is indirect rather than decisive. In addition, Webb has identified systematic biases in earlier infrared datasets caused by limited spatial resolution. By resolving blended sources, Webb clarified which emission came from stars, dust, or background galaxies. These recalibrations do not overturn previous work, but they refine it, reducing uncertainties and narrowing error bars across multiple fields. A scientifically underappreciated capability of the James Webb Space Telescope is its contribution to time-domain astronomy. Although Webb was not designed primarily as a transient hunting observatory, its sensitivity and stability allow it to capture changes in astrophysical systems over time with exceptional precision. Webb has been used to monitor variability in young stellar objects embedded within dense molecular clouds. Infrared light curves revealed irregular accretion bursts, where material falls onto protostars in episodic events rather than steady flows. These observations, analyzed in NASA-led Cycle 1 programs, show that protostellar growth is highly nonlinear, occurring in bursts separated by relatively quiet phases. This behavior alters estimates of protostellar lifetimes and luminosity evolution. It also affects how feedback from young stars interacts with their natal environments, influencing nearby star formation. In exoplanet science, Webb monitored repeated transits and eclipses, detecting subtle changes in atmospheric signatures over time. These temporal variations suggest dynamic weather patterns, cloud evolution, and possible chemical redistribution. Such time-resolved atmospheric measurements were largely impossible before Webb due to sensitivity limitations. Even small temporal shifts matter. Webb's stability allows detection of changes at the level of tens of parts per million, pushing time-domain infrared astronomy into a regime previously limited to optical wavelengths. Another deep scientific contribution from Webb lies in its ability to probe the boundary between galaxies and the intergalactic medium. This interface region governs how galaxies exchange matter and energy with their surroundings, yet it has been notoriously difficult to observe directly. Using background quasars as illumination sources, Webb measured absorption features imprinted by gas surrounding intervening galaxies. These absorption systems reveal the presence of cool, metal-enriched gas extending far beyond galactic disks. Webb's infrared spectra detected ionization states and chemical compositions not accessible at shorter wavelengths. These measurements show that galaxies expel material through outflows more efficiently than some models predicted, enriching the surrounding medium early in cosmic history. At the same time, Webb detected signatures consistent with cold gas inflows, providing observational evidence for gas recycling. The balance between inflows and outflows determines how galaxies sustain star formation over billions of years. Webb's data indicates that this balance is environment dependent, varying with galaxy mass, star formation rate, and redshift. Importantly, these observations connect small-scale processes like stellar feedback with large-scale cosmic structure. They help bridge the gap between galaxy-scale simulations and cosmological models. This area of research is still developing, but Webb's data have already reduced uncertainties in gas density, temperature, and metallicity in circumgalactic environments. James Webb has also contributed to refining the physical limits of observational astronomy itself. Several Webb studies have focused on characterizing the telescope's systematic uncertainties, sensitivity thresholds, and calibration boundaries. By repeatedly observing calibration stars and well-studied sources, Webb teams quantified detector noise, persistence effects, and instrumental line spread functions with high precision. These calibrations allow astronomers to distinguish genuine astrophysical signals from instrumental artifacts. In deep field observations, Webb approached the confusion limit, where faint sources begin to overlap due to finite resolution. By modeling this limit, astronomers determined how much deeper surveys can realistically go before new detections become unreliable. Webb's precise calibration also enabled improved absolute flux measurements across the infrared spectrum. These improvements feed directly into stellar models, galaxy luminosity functions, and cosmological parameter estimation. In some cases, Webb revealed that earlier infrared measurements systematically underestimated flux from extended sources due to aperture effects. Correcting these biases affects interpretations of galaxy brightness and star formation activity. Understanding these limits is not a weakness. It defines where Webb's data is strongest and where caution is required. This clarity increases the scientific value of every observation. One of the most forward-looking impacts of the James Webb Space Telescope is how its data is being used not just to test existing theories, but to forecast astrophysical behavior. Webb is the first observatory whose data sets are precise enough to be directly embedded into predictive simulations, rather than merely compared afterward. In galaxy evolution studies, Webb's measurements of gas fractions, stellar masses, and star formation efficiencies are being incorporated into hydrodynamic simulations to project how early galaxies evolve over billions of years. These simulations now begin with Webb-calibrated initial conditions instead of idealized assumptions. As a result, predicted galaxy morphologies, merger rates, and star formation histories are shifting measurably. In cosmology, Webb's constraints on faint galaxy populations and dust attenuation are being used to forecast future background radiation measurements. These forecasts help refine expectations for next-generation observatories by defining what signals should be detectable and what confusion limits will dominate. In exoplanet science, Webb's atmospheric measurements are feeding into climate and circulation models that predict long-term atmospheric evolution. Rather than static snapshots, scientists are now modeling how atmospheres change as planets cool, lose mass, or experience stellar evolution. Webb's data provides the boundary conditions for these time-forward calculations. This predictive use of Webb data marks a shift from descriptive astronomy to constrained forecasting, where observations actively shape what theories predict next. Another scientifically important but less visible contribution of Webb lies in its role as a benchmark for laboratory astrophysics. Many Webb discoveries rely on interpreting molecular absorption and emission features that must be matched to laboratory measurements under controlled conditions. Webb spectra have already exposed gaps in molecular databases. In several cases, spectral features observed in exoplanet atmospheres and star-forming regions could not be matched precisely to existing laboratory spectra. This prompted new laboratory experiments to measure molecular behavior at temperatures and pressures relevant to astrophysical environments. These efforts involve recreating extreme conditions, low pressure, cryogenic temperatures, intense radiation fields, to refine molecular line lists. Updated databases improve not only Webb analysis, but also the interpretation of data from other observatories. Webb has also motivated revisions in dust grain laboratory studies. Observed dust emission features suggest grain structures and compositions not fully captured by current models. Laboratory work is now exploring non-spherical grains, mixed composition aggregates, and radiation-processed materials. This feedback loop between observation and laboratory physics strengthens the physical foundation of astrophysics, ensuring that interpretations remain grounded in measurable properties rather than assumptions. James Webb has also provided new constraints on fundamental astrophysical scaling relations. These relations, such as the link between stellar mass and star formation rate, or black hole mass and galaxy properties, are cornerstones of astrophysical theory. Webb's data shows that some of these relations hold remarkably well even at early cosmic times, while others break down. For example, the correlation between star formation rate and gas mass appears consistent across a wide range of redshifts, suggesting universal efficiency limits. In contrast, the relationship between black hole mass and host galaxy mass shows increased scatter at high redshift. This indicates that black hole growth and galaxy assembly are less tightly coupled in the early universe than in later epochs. Webb has also refined the mass-metallicity relation by extending it to much lower masses and higher redshifts. The data reveals a steeper slope than previously measured, implying that feedback processes disproportionately affect low-mass systems. These refined scaling relations are now being used to recalibrate semi-analytic models of galaxy formation. Small changes in these relations propagate into large differences in predicted galaxy populations. Another domain where the James Webb Space Telescope is quietly reshaping understanding is stellar feedback at extreme scales. Stellar feedback refers to the influence stars exert on their surroundings through radiation, winds, and explosive deaths. While this process has been studied for decades, Webb has provided the first infrared-resolved measurements of feedback operating inside heavily obscured environments. Webb observed massive star clusters embedded within dense gas clouds where optical light cannot penetrate. Infrared spectra revealed ionized gas fronts, shock-heated regions, and molecular gas being compressed and disrupted simultaneously. These observations demonstrate that feedback does not simply halt star formation, it can also trigger it by compressing nearby gas. In several regions, Webb detected evidence of sequential star formation, where radiation from one generation of stars initiates collapse in adjacent clouds. This pattern had been proposed in theory, but remained observationally ambiguous due to dust obscuration. Webb's data shows it occurring on parsec scales with measurable gas velocities. Webb also quantified energy injection rates from stellar winds and radiation pressure by measuring gas excitation states. These measurements suggest that radiation pressure may dominate feedback earlier than supernova explosions in massive clusters, altering the timing assumptions used in galaxy-scale simulations. This refined picture of feedback affects how galaxies regulate their star formation, especially during periods of intense growth. James Webb has also imposed new constraints on planetary habitability, not by detecting life, but by narrowing the physical environments in which habitable conditions could plausibly persist. This contribution is subtle, but scientifically powerful. Webb measured stellar radiation environments for several low-mass stars hosting rocky planets. Infrared monitoring revealed frequent energetic flares and elevated ultraviolet-linked heating signatures inferred from atmospheric chemistry. These measurements help quantify how hostile certain stellar environments may be for long-term atmospheric stability. In addition, Webb detected carbon-bearing molecules and water vapor in protoplanetary disks at radial distances corresponding to terrestrial planet formation zones. This establishes that key ingredients for habitability are present early, but it does not guarantee retention. For some rocky exoplanets, Webb placed upper limits on atmospheric thickness by failing to detect expected spectral features. These non-detections imply that atmospheric escape or incomplete formation may be common around certain star types. By combining stellar activity measurements with atmospheric constraints, Webb helps define which planetary systems are physically capable of sustaining stable climates over geological timescales. This approach replaces speculative habitability discussions with measurable boundaries. A further area of Webb's impact lies in its role in testing alternative and extended theoretical frameworks. While Webb does not directly probe fundamental physics beyond the standard model, its observations constrain astrophysical consequences of such theories. For example, Webb's measurements of early structure formation place limits on exotic dark matter scenarios. Certain warm or self-interacting dark matter models predict delayed or suppressed small-scale structure formation. Webb's detection of faint early galaxies narrows the allowed parameter space for these models. Similarly, Webb's data constrains variations in the initial mass function of stars. Some theories predict that early stars were overwhelmingly massive. Webb's stellar population measurements suggest a more mixed distribution, limiting how extreme early star formation could have been. Webb also constrains cosmic opacity and photon propagation over long distances. Its precise infrared measurements limit the degree to which intergalactic dust or exotic processes could attenuate light across cosmic time. These constraints do not confirm new physics, but they eliminate possibilities. In science, removal of viable alternatives is progress. One of the last frontiers where James Webb has delivered decisive results is the study of extreme environments that push known astrophysical processes to their limits. These environments are not representative of the average universe, but they test whether physical laws scale consistently under extreme density, temperature, and radiation. Webb observed compact starburst galaxies, where star formation occurs at rates hundreds of times greater than that of the Milky Way. Infrared diagnostics revealed gas densities and temperatures near theoretical upper bounds for sustained star formation. These measurements show that feedback mechanisms eventually impose hard limits, preventing runaway collapse. In regions near active galactic nuclei, Webb detected molecular gas surviving intense radiation fields previously thought to destroy it. This survival suggests that shielding, geometry, and gas clumping play a stronger role than simplified models assumed. These findings revise expectations for how close star formation can occur near energetic black holes. Webb has also measured thermal emission from objects at the boundary between stars and planets, such as brown dwarfs. These observations refine mass-temperature relations and confirm that atmospheric processes in these objects resemble scaled-down stellar physics rather than oversized planetary behavior. By confirming where theory holds and where it begins to strain, Webb defines the operational limits of known astrophysics. Another important class of discoveries emerged only after Webb data underwent repeated reprocessing and independent analysis. Unlike rapid headline results, these findings reflect the depth and durability of the dataset. In several early galaxy surveys, initial stellar mass estimates were revised downward after improved modeling of dust attenuation and stellar populations. This recalibration reduced, but did not eliminate, the tension with formation timelines, showing that part of the discrepancy lay in interpretation rather than observation. In exoplanet studies, reanalysis of spectra revealed that some initially reported molecular detections were influenced by stellar contamination. Correcting for this clarified which signals were truly planetary. This process strengthened confidence in Webb's detections, rather than weakening them. Repeated processing of deep field images also improved source separation, revealing faint background galaxies blended with brighter foreground objects. These refinements improved number counts and luminosity functions used in cosmological studies. This iterative nature of Webb science demonstrates that its impact is not limited to first-look results. The telescope's value increases as methods improve and data is revisited. James Webb has also clarified which predictions made before its launch were incorrect or incomplete. This is a critical function of any major observatory. Some models predicted that early galaxies would be dominated by chaotic, merger-driven growth. Webb showed that ordered structures appear earlier and more frequently than expected. Other predictions suggested that molecular complexity in space would be limited to shielded regions. Webb demonstrated that complex molecules exist in a wider range of environments. Certain expectations about atmospheric uniformity in exoplanets were also challenged. Webb revealed variability, stratification, and dynamic processes that invalidate static atmospheric assumptions. These outcomes do not represent failures of theory, they represent refinement. Science advances by replacing approximate descriptions with more accurate ones. Webb's role in this process is definitive because its observations are not marginal improvements, they are order of magnitude advances in sensitivity and resolution. At this point, the scientific legacy of the James Webb Space Telescope is already clear, even though its mission is far from complete. Webb has not rewritten physics, but it has forced precision where approximation once sufficed. It has expanded observational access to epochs, environments, and processes that were previously theoretical or speculative. It has reduced uncertainty across multiple fields by providing direct measurements instead of indirect inference. Most importantly, Webb has shifted astronomy from asking whether certain phenomena exist to asking how exactly they operate. That transition marks a maturity in a scientific discipline. Future observatories will build on Webb's findings, but they will do so within boundaries Webb has already established. Its data will continue to be analyzed, reinterpreted, and challenged for decades. The James Webb Space Telescope was designed to look deeper. What it ultimately delivered was something more demanding, a universe measured with enough clarity that assumptions can no longer hide behind uncertainty.